Okay, so thank you, everybody. This in this tech chat, we'll briefly see what is the algorithm that Slurm uses to assign priorities and to schedule our jobs. The outline of this talk is the following. So first of all, we will answer this question: when will my job start? There's a very simple utility to look at to answer this question, and then we will look at the why. What is the reason why our jobs start at the time they start? That is, what are the mechanisms that Slurm uses to schedule our jobs. So let's move on. So when will my job start? I recently discovered that actually there is this very simple command that we can use. It's just an option that we need to pass to SQ, and we just get the start date, start time of our job. Let's test it. So I'm on Sunburn now. If I try that, and then yeah. So okay, I will just zoom out a little. Okay, so you can see that we have the usual list of job with another column. We just say, when it's the expected start time for our job. Of course, this may not be true in the sense that if a job which is running now is going to end, then this order, the start time can change. But this is a possible. This is an estimate which for sure is useful. Another option is also to use as control. Show job will also tell us, for example, if I take the last one here, it should actually tell us also a start time, which is here. Okay, but I think that the SQ option is actually a bit more manageable and readable. Okay, so moving back to the flow of the presentation. So once we know what's the start time, what's the expected start time, then we can ask ourselves why is Slurm deciding, has Slurm decided for that start time so far. So the default behavior of Slurm is a first in, first out mechanism. So the jobs which are submitted first are going to be executed first. But if Slurm is configured using this multi-factor priority plugin, okay, then a priority value is computed for each job, and then the jobs will be ordered by priority. Then, depending on the scheduler that we're using, the scheduler algorithm that we're using, it could be that the jobs will be executed strictly following this order, or if we instead have a backfill scheduler, then the scheduler will try to do something clever and start jobs that can start and can execute without delaying any other job which has a higher priority. So for the moment, we'll look at this multi-factor priority plugin and see what are the factors, what are the terms that that contribute to determine the priority value of each job. So this is the formula. Okay, so the job priority is computed as a sum of terms. Each of these terms is composed of basically it's the product of two things: a weight, okay, and a factor. So the weights, all these weights are positive integers, which should be large, like typically 1,000 or 10,000, okay, and the factors instead are numbers which are between 0 and 1, okay. The reasons why these positive integers need to be large is that I think each of these terms is actually converted to integer before summing. So well, this means that if these weights are not large enough, then being these numbers between 0 and 1, if you can have some precision problems. So if you want to differentiate between different jobs, between different users, between basically, if you want these factors to be effective in discriminating the priorities, then yeah, these values need to be large. So now what I'm going to do is going through some of these. We'll look at the first 5, okay, and describe briefly how they work. Okay, so the first one is the age factor. So well, let me just look at the age factor first. So the age factor is the factor that will make your job more likely to start the more time it spends in the queue. So it will increase linearly over time. It will reach 1.0 at priority max age, which means that when your job is, like in this case on Sunbird, 7 days old, then the age term in the age term in the priority formula would be the maximum, which means equal to this value, the priority weight age. Okay, so one thing that needs to be mentioned is that the time spent in the queue while the job cannot run because of dependencies or because it's withheld does not count. Okay, so yeah, all the rest of the factors are basically constant in time. So well, let's see them. So there's a quality of service factor. So each quality of service has a priority factor which is associated with it, and these can be visualized with this command. I don't know if there's if there are other commands. This is the one that I have used. So let's look at them then. So wait a moment. I'll clear my screen. So as account manager, show QoS. So account manager, I need a T. Okay, so we got a lot of information here, but what we are interested in is the second column, okay, which is the priority. So on Sunbird, this is mostly 0, except for the high priority quality of service, and for the development, the dev quality of service. So as I said, the factor that is computed out of this needs to be between 0 and 1. So what actually happens is that the priorities shown are then normalized to the highest, so we get a number which is between 0 and 1, and then that's going to be our QoS factor. Yeah. So there's also a partition factor. So in principle, each partition can have a priority factor associated with it. This can be visualized with as control show partitions. And of course, well, we can look at this now. So as control show partitions. Okay. So yeah, so there is a priority job factor here. I think this is yes. So this is what we saw before. But one thing I want to raise your attention to is also that the partitions have also a quality of service associated with them. So the jobs that are started on those partitions will inherit by default this quality of service, which means that they will also inherit that term in the priority formula. Next is the size factor. Sorry for the noise. So there is also a factor associated with size. So the larger jobs will get a priority increase, which is proportional to the size. So the factor is equal to 1 for a job that requires all the nodes on the machine. This, I think, the reason for this is that smaller jobs will benefit from the backfill scheduling algorithm, while larger jobs will have problems. So I think this is a term that is put in the formula just to somehow try to equilibrate this, to compensate for this. So the next one is the complex one. So it's the fair share factor. And the goal of this term is to prioritize jobs that have been submitted by under-service accounts recently, while deprioritizing the ones from over-serviced accounts. So there are two algorithms for this. There's one which is called fair tree, which is actually simpler. And there was also a classic one. I'm not sure which one is used on Sunbird at the moment. I think it's the fair tree one. I think we can look at this in the looking at the setup, at how Slurm is set up on the cluster. There are two things to keep in mind when talking about fair share. There are two concepts. So fair share terms, fair share values are related to associations. Okay, so and what are associations? From the documentation, we read that the association is a combination of cluster, account, username, and optional partition name. You can look at all of them with these two commands. S share is actually a bit nicer to look at, so I will use that one. So let's look at that. So share, we pipe that into, I will use the -L flag because it gives me a bit more information. So I'll pipe that into less because it's going to be very long. So yeah, so here we can see, actually with this command, I can see only my own association, the associations which are related to my user. I cannot see the association of other users. So for example, I can see that I have one association of my username with this account. So accounts are what they are basically, yes, the project names. And users are, well, just our username. I have a number of accounts where I'm active, so we'll have a number of associations. Here, there is the cluster associated to the association is just Sunbird. There might be other clusters in other setups. So the numbers that are here are actually interesting for what follows. So they will acquire a meaning in the following slides. So let's move on back to the slides. Another thing to know is that the accounts in Slurm actually form a tree. So in principle, an account can have some, accounts have siblings and also children, and then they can finally have users as leaves. So accounts represent nodes in a tree, while instead users represent leaves. Okay, so this is important because this is important to know because the fair tree algorithm actually does it's somehow recursive because it takes into account this tree structure of attributions of shares and usage. Okay, so with this concept, briefly described, we can move on and talk about the algorithm. So, so how does it work? So basically, the computation of the fair share factor for all the users starts in this way. So we set a variable rank to the number of user associations of, So we need to have, basically we are going to rank all the user associations according to some criterion. And well, the way we compute the criterion is the following. Basically, we do this. So first of all, we start at the top level, okay, and we at the top level of the account trees, and we calculate the level fair share for the subtree children. You can actually see the level fair tree in here. Is actually here. It's this column. Okay. Then once we have calculated the fair this level fair share for all the nodes at this level, we sort the children, all the nodes at this level, and then we visit the children in descending order. Okay, and basically we repeat this. We continue the recursion, but the recursion stops when we have a user, we have a leaf in our tree, okay? And when it stops, we assign to the user, actually not the user, to the association with the user, a fair share factor, which is equal to this. So as you may recall, I said that actually the factors need to be between 0 and 1, and well, the current algorithm shows that, well, they need to be, that they are going to be between 0 and 1, because the maximum of this rank is going to be equal to user association count, and this algorithm is going to stop at the last user association, and for this the rank is going to be 0. Okay, so this is the first bit of the algorithm. There are some things that we need to work out. So the problem is, what is this level fair share? How is it computed? So it's computed as S over U, where actually S is the share that we are that we assigned to a given account, to a given node in the tree. Okay, and yeah, it's actually a ratio of the resources, let's say, that were assigned to that node over all the resources that were assigned to the parent, let's say, so to that node and its sibling. Okay, and this is for the resources that were assigned. So the fair share that was, I don't know, it's also called the fair share. So it's the amount of resources that theoretically that association, that account actually should be using. And the U instead is the term. It is the amount of resources that were used actually by the association, by the account. Okay, and this is computed in the same way. So there's a normalization of the usage versus the usage of the whole family, let's say, the self plus siblings. Okay. If something's not clear, then we can get back to this. There's also a link to the documentation, which is quite clear. Requires a bit of time to understand. Yeah, but one thing that we still need to see is how this U row is computed, because it's not as straightforward as it seems. As I mentioned before, the usage that I mean, there's this term in the priority calculation only takes into account recent usage. How does it work? So this is actually something that needs to be, that is not clearly expressed in the documentation, but at least for the classic fair share, this is basically how it works. So the resource usage, which is that's used in this formula, is something a bit more complex than just the resource usage that historically has happened on the machine. Is like a decaying usage. So the term, basically the value that we are going to use is going to be the sum of the usage in a last period plus the usage in the previous period times a decay factor, and so on. Basically, well, there's going to be, actually there should be an ellipsis here. There should be many times more. Basically, well, there's a decaying factor that makes sure that we don't take into account usage that happened too far in the past. Okay. So this D is set up. The value of D is chosen so that it gives a half-life as set by this parameter, which we will be looking at soon. Yeah. So let's look at a couple of things now. So first of all, this priority priority decay half-life. Where is it defined? We can look at the configuration file on Sunbird, and we will have it. So it's actually in this directory, and it's called slurm.conf. So here we have a number of parameters. They are sort of namespaced. So the parameters that we are interested in usually start with priority, and here they are. So for example, we can see all the weights. Okay, so there's a priority decay half-life, 7 days. Okay, so it means that the term in this, so the half-life used in this formula is going to be a week. Okay, and then yes, we also see that, for example, when I was talking about the age term, we see that the max age, the maximum age, is actually 7 days. Okay, when our jobs are getting 7 days old, after they are 7 days old, their priority is not going to increase anymore. At least as far as the age term is concerned. And yeah, and then here you can see also all the other terms. Okay, so for example, let me just get back to the formula at the beginning. Was here. So you see there's a number of these factors are shown in the slurm.conf file, and you can see that these are pretty large numbers. You can see that the fair share is the largest here. And actually, I mean, it's the same as the quality of service. Yeah, and actually, the job size. Yeah, the job size factor is also large, but consider that it's really rare that a job will get this value, because as I said, this value is obtained only when a job is submitted with having the size of the whole cluster, which is actually not possible. So okay, we'll just move on to the last slide. Okay, so sorry, there's another slide before the last. So I'm going to talk about some tools that are going to help us. So S-share -L, we already saw what it tells us. So I will look at this again. So I'm not aware of the meaning of everything, every column here. So as you see here, there's a, as I mentioned here, there are the associations. You can see only your own associations. I think that if you run this command on your own, on somewhere on your own, you will have possibly you will have your own values for your own accounts, for your own username. And well, the important bit is this. So this is the fair share factor that has been computed for this association, which means that, for example, for this association, my fair share value is going to be 0.85 multiplied by 10,000. 10,000 is the value that we saw before in the slurm.conf file. Yeah, this level FS, this level fair share is the one that it's used to order my my account with the others. It's a pretty large number, which means that the fair share associated to this association was actually larger, much larger than the usage. Okay. So, well, this means that I rank pretty high. So there's the fair share is pretty close to 1. So it means that that this fair share mechanism is going to privilege this association. Okay. Another tool that we can use, and it's really helpful, possibly more than S-share, is S-prio. S-prio -L does the following. It just looks at the whole queue, and it tells me for each job what is the priority that I get, so the overall priority, and it also tells me all the contributions of all the terms. Okay, so I know, for example, that this job has been in the queue for very long, it seems, because of a very high age term. Yeah, we know that. I think if we look back at the maximum value of this age factor, it can be 1,000. Then the fair share is really high as well. Job size, yeah, I mean, it's impossible. It's in principle possible to get back the size of a job looking at just the job size priority term. And well, the partitions are equal for everybody. I think that if we had any jobs submitted with to the development partition, then we would have also a contribution from the quality of service. Eventually, there's a nice factor which I haven't talked about because, well, but just to mention it, it's something that a user can set to positive number, and it basically will be subtracted from the priority. So if you want to be nice, if you want to if you want to delay a job of yours from starting, then you can change this nice parameter for a job. You can do this with the S control, and this will just reduce the priority of a job. If we want to check, I mean, there's another way to check what are the weights associated to each of the terms in the formula, and it can be done simply with choosing S-prio with this with the -W option. I hope you can see. Yeah, so well, it just tells us what we already knew, that the age is 1,000, fair share 10,000, etc., etc. Okay, so The only other thing that participates in determining when our job is going to be executed is actually the backfill. In the scheduler itself, there are two algorithms that can be, at least two algorithms that can be used in Slurm. The backfill is actually the default one. So the way it works is that at some kind of events, so at job submissions, so completions, also configuration changes, a fast job scheduling is attempted. And by fast means that a small number of jobs in the queue is looked at. Also, does some limitation. Let's say the search space for new jobs to run is not going to be is not really large. Then every 30 seconds is the default. A larger, sort of a more time-consuming scheduling attempt is done. Backfill scheduling is indeed a time-consuming operation. It's not exactly clear to me, but you can see that actually, well, backfill scheduling needs to work in this way. So it needs to find jobs that can start without delaying the expected start time of any higher priority jobs. So it needs to of course compare all the resources and see. I mean, I think it's a complicated puzzle that the backfill scheduling algorithm needs to solve. So with this, that's the end of my presentation, and I thank you for your attention, and I'm open for questions. Hopefully I will be able to answer them. So thank you very much.